And now, on to the presentation. Innovative Isolated RS-485 SPI and LVDS Communications. It's my great pleasure to introduce today's presenters. Our first presenter is Richard Anslow, Product Applications Engineer, Analog Devices. Richard Anslow is a Product Applications Engineer at Analog Devices, where he works with isolated interface solutions for industrial applications. He earned both his Bachelor's in Engineering and Master's in Engineering from the University of Limerick, Ireland. And joining him today is Eric Benedict, Senior Applications Engineer at Analog Devices. Eric Benedict is a Senior Applications Engineer at Analog Devices, and he earned his BSEE and MSEE from Purdue University and an MSEE and PhD from the University of Wisconsin-Madison. It's with great pleasure I now turn this special session over to Richard to begin. Richard?
Thanks, Chris, and welcome everybody. As Chris mentioned, my name is Richard Anslow, and I'll be guiding you through the first half of today's presentation. My colleague Eric will then take over for the second half of the presentation. The objective of today's presentation is, firstly, to discuss our recently released RS-485 and LVDS products. In particular, we will look at the benefits that our certified EMC-hardened RS-485 transceivers provide for military and aerospace applications. We will then look at our isolated LVDS product family, outlining benefits for isolation of analog front ends and high-speed backplane extension. My colleague Eric will then discuss isolating ADCs for industrial test and measurement systems. And then finally, Eric will provide you with a summary of our combined interface and isolation portfolio. This portfolio in particular offers more features and enhanced performance with the addition of legacy linear technology products. Moving on, in this first section we will discuss our isolated RS-485 in military and aerospace applications. Lightning strikes to jet airliners are common, in fact about once every 1,000 flight hours. As a result, many airplane manufacturers specify DO-160 Section 22 lightning-induced transient susceptibility as a requirement for critical systems like guidance, radars, communication, engine control, and heat and air controls. The DO-160 Section 22 lightning standard simulates the transient voltages and currents introduced into avionics as a result of the magnetic fields generated by direct lightning strike through the aircraft frame or fuselage. As shown in the figure below on the right-hand side, the communication interfaces for flight control systems can be implemented on an RS-485 physical layer. Communication interfaces for aircraft engine management control can also be implemented with an RS-485 physical layer. If the RS-485 communication interface is damaged from indirect lightning, then the engine condition monitoring will fail in service, and our closed-loop feedback for flight control systems can be compromised. This slide shows that aircraft equipment is divided into 3 zones, and each zone has an associated electromagnetic compatibility or EMC environment. The most severe EMC environments are located in the Category A and Category B zones, which are areas of the aircraft that are not environmentally controlled. So flight controls avionics are located in the Category A and Category B zones. These areas are harsh EMC environments with DO-160G Section 22 lightning Level 3 or Level 4 protection required. Commercial aircraft EMC requirements are much more stringent than IEC 61000 industrial standards requirements. The plot on the bottom right-hand side shows that the peak currents for the DO-160G Level 4 tests are much greater than the standard industrial surge IEC 61000-4-5 peak currents. The waveform shape and rise decay times for the DO-160 standard are significantly longer than those specified by the IEC 61000-4-5 standard. So to protect against DO-160G lightning require multiple components. On the left-hand side we see a typical array of external EMC protection components such as TVSs, TBUs and TIFs, which are used in combination to protect against harsh EMC events. So this circuit requires the careful selection and electrical matching of the EMC protection components to the RS-485 interface. The high voltage breakdown characteristics of the RS-485 device need to be matched to the protection interface. The design needs to be tested and compliance confirmed against the DO160 standard. If the design fails, then the engineering designer must enter an iterative process to pick better electrically matched components. This can be a costly and time-intensive process. The right-hand side of the slide shows Anaroグ디바이스의 ADM2795E-EP, which integrates digital isolation, RS-485 transceiver, and EMC protection in a single package. This is industry's most robust and compact solution, which results in a 70% PCB board area saving for space-constrained customers. This design also reduces the design cycle time, as the system designer does not need to complete several PCB iterations to get to the desired solution. The non-isolated ADM3095E-EP is also available, which combines the same high level of robustness protection in a single package. A little bit more detail on the tested and certified DO160 Section 22 Lightning Surge solution. The ADM2795E-EP was tested and certified in an external EMC test house. Testing was performed to both ground 1 across the digital isolation barrier and to ground 2 exposed RS-485 bus pins. For testing to ground 1, Anaroグ디바이스의 I-coupler isolation technology is robust to the most extreme level 4 DO160G waveforms 3, 4, 1 and 5A. The ADM2795E-EP was not originally designed for military aerospace applications, so as a result we need to add 33 ohms of current limiting resistance to the ground 2 pins in order to protect against the bus pins against these extreme levels of lightning surge, which are much larger than the IEC levels of surge which I stated in the previous slides. Certification is available on request for these parts from your local Anaroグ디바이스의 FAE. I'll just move on to discuss our isolated LVDS solutions. Example of an application that will require isolated LVDS is extension of a high-speed industrial backplane. So such a backplane could be used to link PLCs and I/O modules with higher bandwidth to support larger numbers of modules for increased numbers of inputs and outputs. With larger numbers of modules, it also becomes attractive to link sections of the backplane via cable interconnects. In a harsh industrial environment, any exposed external I/O must be protected against hazardous voltages. Using the ADN4650 LVDS isolators, both the high bandwidth and necessary high robustness can be provided. For a cable interconnect, one relevant question is, how long can that cable be? Among other parameters, this depends on the data transmission speed and the signal jitter. The low jitter of Anaroグ디바이스의 ADN4650, 4651 and 4652 LVDS isolators ensures that more of the jitter budget can be used to account for the cable effects, allowing the cable to be as long as possible. So in the following slides, we'll actually examine a bit more about the background theory for signal jitter and present an example application system where we show that the jitter budget for an isolated analog front end, not a lot of the jitter budget is actually consumed by the isolated LVDS solution. A second example where LVDS isolators can be used is for isolating analog front ends. An analog front end might need to be protected from hazardous voltages, for example, accidental connection of expensive lab equipment to mains reference systems. Measurement accuracy for AFE may also need to be preserved in noisy environments. To avoid interference, individual analog front end channels may need to be separately isolated. High-speed communication across a backplane or isolation of high-speed analog front ends. Attention must be paid to the topic of jitter as we previously mentioned. So our isolated LVDS family feature a comprehensive analysis of jitter performance. So just a little bit of background here. Jitter refers to the timing variation of edge transitions from their ideal transition time. If many edge transitions are overlaid, as seen with an oscilloscope set to infinite persistence, we can visualize this timing error as a blurring of the edge transition. To formally analyze and quantify the jitter, a histogram is compiled from the edge transitions, as shown in the example here. Some analysis is needed to put a limit on jitter because total jitter is composed of a random or unbounded component as well as a bounded deterministic component. This means that peak-to-peak total jitter will gradually increase the longer that transitions are observed, or rather the greater the sample size. So random jitter arises from physical phenomena such as thermal noise, but by contrast, deterministic jitter is fixed and originates from several sources such as duty cycle distortion or skew, intersimple interference, and data rate independent jitter. An analog front-end interface is provided by the middle board shown above, which uses two ADN4651 LVDS isolators. The CN0388 LVDS isolator board connects directly to the standard AD7960 evaluation board and SCP H1 high-speed system demonstration platform. You can source these PCBs directly from ADI. In this demonstration platform, the high-speed ADC AD7960 5 MHz sample clock and the 300 MHz reference clock and 600 megabits data from the FPGA is all isolated through the ADN4651 LVDS isolator. The ADN4651 additive phase jitter is sufficiently low that it does not affect the ADC performance, even when isolating the sample clock. In addition, implementing the galvanic isolation improves the ADC performance by removing digital and power supply noise from the FPGA circuit. So this demonstration platform can be run with or without the LVDS isolator board. The LVDS isolator timing performance, including jitter, has negligible effect on the system performance. So a number of key features for our recent released LVDS isolators. As well as the 600 megabits data rate and rigorous timing performance that I mentioned already, the ADN4650 family also includes a 5 kV RMS withstand isolation rating and is rated to VE0884-10 for 10 kV surge with 300 volts RMS reinforced working voltage. The isolated LVDS solution is 4 times faster than existing digital isolators. And in comparison to existing solutions, this isolated LVDS solution is highly integrated and is much easier to use and is lower cost versus competitive solutions such as fiber, discrete transformers, capacitors, and existing digital isolators. So, thank you everybody. I'll now hand you over to my colleague Eric Benedict.
All right, thank you, Richard. All right, so let's talk about isolating successive approximation register analog to digital converters. So industrial or tested measurement systems require isolated data acquisition channels. Reasons for the isolation may include breaking ground loops, noise isolation, protecting equipment or users, and or level shifting between different ground reference domains. While analog isolation options are available, for many applications, providing the isolation at the digital interface is the best choice. Successive Approximation Register, SAR, analog to digital converters make up a significant portion of the market in the 100 kilosample per second to 5 megasample per second data acquisition space and can offer up to 24 bits of resolution. With higher sample rates and resolutions, a higher speed communication port is required. In SPI interfaces, the data is read or written based on the clock edges generated by the master. In non-isolated applications, an upper limit for the clock frequency is often set by the combination of the master's setup time and the slave device's response delay, since the bus transport delay is virtually zero. When the interface is isolated with a standard digital isolator, every input edge event is transferred across the isolation barrier, and these transport delays must be included in the maximum clock speed calculation. Products which specify throughputs of 150 megabits per second can often have propagation delays of as much as 14 nanoseconds, and this adds up to a significant limitation on the clock frequency. For example, when using a standard 150 megabit per second digital isolator, the round-trip timing breaks down as follows. The 14 nanosecond S-clock propagation delay to the isolated side ADC. the 8 nanosecond response of the ADC, the meso response back across the isolator, and the setup time required before the next clock edge. All of this adds up to a maximum clock frequency of approximately 25 megahertz. If we were to consider an isolated application which will require 18 bits sampled at 1.25 megasamples per second, it is clear that a standard isolator won't work. Transferring 18 bits at 25 megahertz will consume 720 nanoseconds out of the 800 nanosecond sampling window, and when the ADC's acquisition time is included, we've run out of time. One common solution to reduce the impact of this transit delay is to loop the clock signal back from the isolated side. In this solution, the master is configured to use the delayed clock when reading the meso data. This configuration requires a non-standard SPI implementation for the master and requires an additional isolation channel. Because the meso D clock is delayed to align with the readback data, the transit delay across the barrier is now effectively removed from the SPI bus's maximum clock frequency calculation. However, now the maximum frequency is determined by the timing skew and distortion in the isolator. Depending on the isolator technology used, the maximum clock frequency will range from as low as 6.25 megahertz for the optocoupler-based isolators up to 25 megahertz, which is possible with a single digital quad isolator with 2 reverse channels. Improvements in the power consumption and clock speed may be obtained by precisely delaying the clock signal at the logic side instead of returning it through the isolated side clock. The meso D clock is delayed by the amount of the round-trip propagation. Since the return isolator isn't used, the power consumption is proportionally reduced. Because the delay timing is trimmed at production, the timing mismatch between the delayed clock and returning meso data is considerably reduced. This increases the usable SPI clock frequency to 40 megahertz and allows for sample rates up to 1 megasample per second. Unfortunately, for our example 18-bit 1.25 megasample per second application, we will still need another solution. In this, the solution is to use the LTM-2893, which approaches the problem of isolating a SPI interfaced ADC in a different manner. The LTM-2893 uses a logic side SPI slave and an isolated side SPI master to handle their respective SPI interfaces, and then only transfers the conversion start and resulting data across the isolation barrier. A SPI read sequence using the LTM-2893 will proceed as follows. The master controller lowers its conversion start line, which triggers the logic side slave to raise its busy line and command the isolated side master to initiate the conversion by lowering its conversion to line. When the ADC's conversion is complete, the ADC lowers its busy line, which allows the isolated side master to read the ADC data and then send it across the isolation barrier to the logic side slave. Once the logic side slave has buffered 2 data bits, it lowers its busy signal to signal the master controller to read the data. This allows the LTM-2893 to seamlessly isolate the ADC with no reconfiguration of the master controller's ADC interface. When using a SPI mode 00 and clock frequencies up to 100 megahertz. Depending on the ADC, this can allow for sample rates greater than 1.5 megasamples per second. Earlier, Richard explained about the impact that jitter can have on the conversion quality. The LTM-2893's conversion start has a very low jitter of only 30 picoseconds RMS. The LTM-2893 includes a second data readback channel and 3 additional control lines. The LTM-2893 has a very high common mode transient immunity of at least 100 kilovolts per microsecond under dynamic conditions. This means that the LTM2893 will reject common mode transients even when it is actively transmitting data across the barrier. Finally, the LTM2893 is very compact with a 15 by 6.25 millimeter footprint, which provides a generous 9.2 millimeter creepage distance. Coming back to the sample application I mentioned earlier, we can now look at a solution. For the ADC, the AD4003 is a good choice. This differential input ADC provides the required 18 bits of resolution with a 2 megasample per second throughput rate, low power, and many other features packed into its small 10-lead package. The AD4003 offers many different digital interface options. However, its chip select 3-wire with busy indicator mode is the one which is compatible with the LTM2893. In this mode, SDO will be high Z while the conversion is in process, and once the conversion is complete, the AD4003 will pull SDO low in order to signal that the data is available to be read. To use this mode, connect the AD4003's SDI pin to the logic supply voltage and pull the SDO pin high using a 1K pull-up resistor. Connect the 4003's SDO to both MISO A2 and BUSY2 on the LTM2893. The LTM2893's BUSY2 input will act on the first falling edge of SDO and ignore the subsequent transitions while the data is being read in through MISO A2. The LTM2893 is configured by the microcontroller with its application-specific parameters by using the SPI bus to write to the LTM2893's configuration register. The microcontroller uses the chip select pin to talk with the LTM2893 and the slave select pin to access the remote ADC. In this application, the LTM2893 should be configured to use the 100 MHz S-Clock2 frequency and a single 20-bit word. With this configuration, the 2 upper bits will be discarded. Here is a scope image of a data conversion signal showing the isolated and logic side digital signals when the AD4003 is sampling at 1.25 megasamples per second. All right. The LTM2893 works well for applications beyond just isolating a single ADC. For example, the LTM2893's 3 control lines can be used to control or configure isolated side devices, such as an analog multiplexer or a programmable gain amplifier. While this displayed application has the control lines all directed from the logic to the remote side, they may be individually configured to be either forward or reverse, which allows even more application options. The second MISO channel of the LTM2893 allows for simultaneous ADC sampling, which is required in many applications, including the measurement of instantaneous power. Okay, so to conclude today's webinar, I'll take a few minutes to introduce you to a selection of Analog Devices combined portfolio, which includes the interface and micromodule isolator parts from Linear Technology. So our standard RS-485 transceivers include full and half duplex parts, which support a supply voltage range from 3 to 5 volts, as well as a single supply voltage parts whose performance is optimized for either 3.3 or 5 volts. Of note, the AD3066E features a separate VIO supply pin, which provides compatibility with lower voltage logic interfaces. There are also part options with lower speed and edge rates for reduced EMI and high-speed transceivers for applications requiring data rates over 50 megabits per second. The LTC2856 and ADM3066E families include a small 3x3 millimeter DFN package option, and the ADM3066E also offers a 12 kilovolt IEC ESD rating on its bus pins. In our fault-protected RS-485 area, the RS-485 transceivers need to be able to operate in rugged environments. Our fault-protected transceivers do just that. Most of these parts have a plus-minus 25 volt common mode range, which is more than double what is specified by the RS-485 standard. All of these parts are ESD protected to at least human body model levels. There are 9 different parts which meet the IEC Level 4 ESD requirements. All of the LT and LTC parts are fault protected to plus-minus 60 volts, which allows for easy coordination of appropriate application-specific external protection networks while maintaining a low output capacitance. Earlier in this webinar, Richard introduced the ADM3095E, which integrates this full protection network and allowed it to be certified for Level 4 IEC, ESD, EFT, and Surge with no additional components. Time to include isolation in your RS-485 interface. We have many options to best fit your application's needs. There are full and half duplex options with speeds from 500 kilobits per second up to 20 megabits per second. If your application already has isolated power, we've got several choices which just provide the isolated transceiver, including the ADM2795, which Richard discussed earlier. If your application doesn't have an isolated supply available, we've got options which provide their own isolated power, such as the ADM2587E and ADM2687E. And finally, we've even got parts that can provide up to 1 watt of available power for your isolated side application circuitry. The LTM2885's 6.5 kV dielectric rating allows isolation with up to a 690 volt RMS working voltage. In order to have the best signal quality and network performance, the RS-485 bus needs to be terminated at each end. Analog Devices now has transceivers which include controllable integrated terminator resistors. There are applications where both RS-232 and RS-485 are required. Some applications use one interface for configuration or service, while the other is used for normal applications communications. Other applications may need to convert between RS-232 and RS-485. With options for a different number of RS-232 and RS-485 transceivers, integrated termination, and half full duplex control, the LTC2870 family of multi-protocol parts will solve these problems in a single IC solution. Other applications may simply just require multiple RS-485 or 422 channels, and again, we offer different choices with either quad receiver drivers or dual transceivers. The LTC 1589 and 1519 will receive over 50 megabits per second, and the LTC 1688 and 89 drivers will go up to 100 megabits per second.
Okay, for I2C, oh my. Okay, it appears we've got some technical difficulties, and the slides graphics showing the different parts are not coming through correctly. Okay, I guess you can download the slide deck with the full graphics by clicking on the green resource link below. So I guess I will go ahead and talk, assuming you're looking at the downloaded deck. Give you a second here. All right, so the Inter-IC or I2C interface is another popular interface, especially for accessing power management or sensor applications. Often, these applications will require isolation, and we've got several different options to best meet your application needs. There are options with unidirectional or bidirectional clocks. The bidirectional clocks will allow I2C masters to be present on either side of the bus, while the unidirectional clock parts require that the isolated side can only have slave devices. Again, like the isolated 485 parts, there are many different power options available. Parts for applications which can provide isolated power, a part which can provide just a small amount of isolated side application power, and parts which offer different options for fixed, adjustable, and bipolar output with up to 1 watt available to the application load.
All right, and finally, we have a selection of parts which are suitable for isolating SPI bus applications with powered and unpowered options. Depending on the SPI bus clock speed, there are several different options available, including the LTM2893 and or the ADUM3150 or 4150, which were discussed earlier. When your application requires isolated power, again, we have different options. The SPI versions of the LTM2883, 2886, or 2887 all offer the same output power options for fixed, adjustable, and bipower output power as their I2C versions. The ADUM 3471 and 4471 provide a switching regulator which, when combined with an external transformer, will supply up to 2 watts total power. Well, thank you. That's all I have for today, and I'll now hand it back to Chris for the Q&A.
All right, thank you, Eric. And now before we begin with today's Q&A, please fill out the feedback form that's opened up on your computer. If your pop-up blockers have prevented the form from launching on your computer, you can click on the red survey icon at the bottom of your screen. And to complete the form, please press the Submit Answer button at the bottom of the page. Thank you in advance for filling out the feedback form. Your participation in this survey allows us to better serve you. We're going to now move on to the question and answer portion of our event. As a reminder, to participate in our Q&A session, just type your question into the text box located to the right of the presentation window, or click on the Q&A icon at the bottom of your screen, and then click the Submit button. Please note that we'll try to get to as many questions as we can with the time that we have left, but if we don't get to your question today, someone will be getting back to you after the program is over. So let's move on with our first question. Our first question is going to be for Richard. Richard, are isolation and EMC certification available for the ADM 2795 EEP? And if yes, what certification is available?
So safety and regulatory compliance information is available on analog.com/iCoupler. Also, DO160 Section 22 Lightning Surge certification for the ADM 2795 EEP and ADM 3095 EEP is available on request from your local Analog Devices Field Applications Engineer.
All right, thank you, Richard. We have another question for you. Does ADI provide reference evaluation boards for the isolated LVDS AFE example presented?
Yes, so Analog Devices provides sample reference evaluation boards for all of the boards shown in the example AFE. So the CN0388 circuit evaluation board is available. We also have an AD7960 evaluation board and also an STB-H1 system demonstration platform.
All right, thank you, Richard. We have a final question here for Eric. Eric, does the LTM2893 support ADC chaining?
Yes, thank you. Yes, it does. You just need to stack up your parts with the SDO connected to the SDI as you form your chain, and then make sure that you configure the LTM2893 so that the number of words and the word size multiply out so that your transaction has the right number of bits for the total number of devices that you're chaining.
All right, well, thank you, Richard, and thank you, Eric, for a great Q&A and great presentation. That is all the time that we have for questions for today. Once again, if we didn't get to your question, we will be getting back to you after the program is over. And for more information related to today's webinar, please visit any of the resource links available in the green folder icon at the bottom of your screen. And also within the next 24 hours, you will receive a personalized follow-up email with details and a link to today's presentation on demand. Once again, we'd like to thank you for attending today's webinar, Innovative Isolated RS-485 SPI and LVDS Communications, brought to you by Tech Online, Analog Devices, and Arrow. This webinar is copyright 2018 by AspenCore. The presentation materials are owned by or copyright by Tech Online, Analog Devices, and Arrow, and the individual speakers are solely responsible for their content and opinions. On behalf of our guests Analog Devices, and Arrow, I'm Chris Keach. We'd like to thank you for joining us, and we hope you have a great day.